Hi, my name is Bryant and I am a development engineer for Texas Multicore Technologies. In this video, I will be walking you through the writing and compiling of a more advanced program in SequenceL. This video will primarily focus on writing what are known as index functions as well as manipulating sequences from within C++. This video assumes that you already have SequenceL installed on your computer and you have seen the previous videos in this series. I will also be making use of the CImage library in this video, which is linked to in the video description. To demonstrate these concepts, I will be using SequenceL to implement Conway's Game of Life. Conway's Game of Life is a cellular automaton based on 4 simple rules. Any live cell with fewer than 2 live neighbors dies, as if by underpopulation. Any live cell with 2 or 3 live neighbors lives on to the next generation. Any live cell with more than 3 live neighbors dies, as if by overcrowding. And any dead cell with exactly 3 live neighbors becomes a live cell, as if by reproduction. More information can be found on Conway's Game of Life at the link in the video description. A powerful feature of SequenceL, both in terms of making code easier to read and write, as well as improving the performance of SequenceL programs, is an index function. Index functions allow the programmer to define a function that returns a sequence element-wise, similar to the way definitions are written in mathematics. To start, we will make a new SequenceL project and we'll call it Game of Life. And I will be using the Microsoft Visual Studio C++ compiler. The project is created with the 2 key parts of a SequenceL project, the main SequenceL file and the main C++ driver file. I'll start by writing the SequenceL code. For reference, I'll put the rules for the Game of Life as a comment at the top of the file. The SequenceL code for this program will consist of primarily one function. This will be the function that evolves the simulation from one state to the next based on these 4 rules. We'll represent a state of the automaton by a 2-dimensional sequence of integers, where a 0 indicates a dead cell and a 1 indicates a live cell. To start, we can call the function life, and it's going to take a single argument, which is of depth 2. This is the current state of the automaton. The result of this function is the updated state, which is a 2-dimensional sequence of integers, so I will be implementing this function as a 2-dimensional index function. To indicate that, I use square brackets and the 2 free variables I and j. What this index function will allow us to do is to specify the value of the next state at each position of the next state. The first thing we need is the number of neighbors bordering the current cell. To compute this, I will use a let body to define num neighbors. A let body allows the SequenceL programmer to define values that are local to the current function. To define num neighbors, I will add up all of the surrounding cells. Once we have the number of neighbors, we can start to define the body of the function. The first cases I will handle are the border cases. SequenceL uses 1-based indexing, so if I or j is equal to 1, or the size of the cells, then the function will return 0 for that location. This is basically zeroing out the border. The next case is when a cell will die. This is either from under or overpopulation. Therefore, the current location is also 0 when it has less than 2 or greater than 3 neighbors. Something important to point out at this point is that there are no executability conditions on num neighbors in the let body. This may look like it will cause an out-of-bounds error on execution. However, definitions in the let body do not get executed until they are needed in the body of the function. When I or j is equal to 1, num neighbors is never computed. This is a very subtle yet very powerful feature of SequenceL. Definitions in the let body are only executed when they are needed, and at most only once. The next case is when a cell is alive. A cell is alive either when it is already alive and has 2 neighbors, or if it has 3 neighbors. In the final case, otherwise, return the current cell and do nothing. That's it for the state progression function. Before we compile it, however, we can do a quick test in the interpreter. I'll hardcode a small blinker state and use that to test. It looks like the function is working properly, so I will set up the intended use in the project properties. The only argument is a depth 2 sequence of integers. And now I'll go ahead and compile the project. The SequenceL compile succeeds, and as we expect, the C++ compile fails, since we haven't updated the C++ driver. Now we can move on to the C++ code. First, I'll go ahead and add the includes I will need. I'm also using a utils library to read files and the CImage library to display the grid state. The link to the CImage library is in the video description. Here we're including the generated header file from the SequenceL compile, and one more namespace to make the code cleaner. Again, in order to use all cores, we will set the number of cores to 0. We'll be reading the location of the input file from the command line. The input file will contain the initial grid state as a sequence of comma-delimited zeros and ones on a single line. And for ease of implementation, we will assume that the initial grid is always a square. Here, we will fill a vector with all of the values of the cells in the input file. I will then use the sequence pointer constructor to convert the vector into a two-dimensional sequence of integers. First, I specify the dimensions of the sequence using a zero-terminated array of integers, here called grid dims. And then I declare a sequence of sequences of integers called initial grid, and pass the constructor a void pointer to the sequence data and the dimensions of the sequence, grid dims. The result will also be a two-dimensional sequence of integers. Now I will set up the window and image to display each state. The program is going to run until the window is closed. At each step, the screen will be cleared. The next state is computed using the compiled SequenceL function, and then that state is written to the screen. Here, I will iterate through the result sequence and draw a black circle on the screen at the location of every live cell. You'll notice that even in C++, the sequences use one-based indexing. After each iteration, the result is copied into initial grid. Before we can compile the project, I have to add some C++ libs that are required by CImage. Once that's done, we can compile the project. After compilation, we can run the program. I'll start with a Gosper glider gun. This simulation is 100 cells by 100 cells, and is your basic Gosper glider gun, as well as a couple other 3 and 2 period oscillators. We can also run a more complicated seed, which is 1000 by 1000 cells. This is a much more complicated game of life seed and is often used as a stress test on game of life implementations. And all of this is being done using the single SequenceL function we just wrote. In this program, SequenceL index functions allowed us to easily implement Conway's game of life in a straightforward manner. We will focus on auto-parallelization in a later video, but SequenceL also automatically parallelized the generated C++ source code, which allowed such a simple implementation to perform reasonably well. We also saw how to pass data to SequenceL easily using the sequence pointer constructor, and how to access the resultant sequence data from C++. In the next video, we will explore SequenceL's ability to automatically take advantage of multiple cores in a multi-core environment. Thank you for taking the time to watch this video. If you have any questions or comments, feel free to comment on this video or contact us via our website, which is linked to in the video description. If you're interested in learning more about SequenceL, be sure to subscribe to this channel.